Hello and welcome to today's session, Grade 12 learners. My name is Themba Ncube. Today is Physical Sciences. This lesson is proudly brought to you by Gauteng Department of Education, GDE, in collaboration with Saibono Discovery Center. Right. This is our last push for today. We shall try and use the time that we have to try and cover as much as we possibly can. However, we shall be focusing our attention on, the basics, just to remind ourselves of what is important. Just to get interactive with us on our WhatsApp line, the number is 064 748 8913. Just to repeat the number once again, 064 748 8913. Use the chat platform just to get interactive with us. Share your comments, clarity seeking questions, inputs. However, we shall only be using those text messages on the WhatsApp platform. No voice notes or your videos shall be used for the purpose of our engagement. Right. Now, this is the eve of our physics paper 1, the National Senior Certificate. We have come up to thus far. So we shall be using this session just to try and, remind each other of what is important and also try to, boost our confidence in terms of, the marks, where you can get the easy marks, So pay careful attention. We shall have 2 segments in this session, and in each one of those, we'll try and look at different aspects of the first paper. Right. Just to get us started, nothing new. The paper is still 150 marks with a duration of 3 hours in total. Now, the sections that will be examined in the paper are as follows. We've got the mechanics that carries the bigger chunk of the marks in paper 1, which is 63. So your mechanics will encompass your Newton's laws from grade 11, your vertical projectile motion, your linear momentum and impulse, your work, energy, and power, right? So that's about 5 questions, the first 4 questions in the long section of section B. And then we've got sound, waves, and light, which is an overlap of EM radiation as well as your Doppler phenomenon and applications thereof. And then that carries 17 marks, right? And then electricity and magnetism, which has got a total of 55. Now, electricity and magnetism is broken into your electrostatics, your electric circuits, your electrodynamics. So those are the 4 subsections under the theme of electricity and magnetism with 55 marks. And then last but not least, the photoelectric effect, optical phenomenon, which has got an overlap with the light, waves, and sound as well. But the sound will be primarily focused on the Doppler phenomenon, and then the part which has to do with EM radiation and light will focus on photoelectric effect, which is 15 marks. So the grand total is 150 with an allocation of 3 hours, right? Okay, there's nothing new there. And then what are the key things that maybe each and every one of us needs to remind themselves of? The first one is the easy marks in as far as the definition. Pay attention to the action verbs. Explain, define, state. It could be 2 marks or 1 mark. If you're given a statement, you are supposed to identify a term that fits that description, which will be in the form of a definition, or you'll be asked to state a principle, define a concept, or explain a simple concept in physics. So that's all or nothing, which gives us a total of 2 marks at most, right? But then remember, once again, the guide that we use in terms of the examination guide is your examination guide of 2021. So just draw your attention to that in as far as what is acceptable by the examiner, right? So the long section of the long questions in section B, which is 130 marks that we referred to earlier, will comprise of a definition or 2 per question. So if in section B, for argument's sake, we've got 9 questions, it means there can be a minimum of 2 questions, 2 marks per question in those in each of those questions in section B. So if you calculate that, it can give you easily, a lot of marks. So that's our easy marks or our low-hanging fruit, right? Now, always refer to the formula sheet or the data sheet that will be attached for your use as stipulated in the instructions, right? Now, this one, it's a recommendation. It also serves in terms of maybe how one can actually, manage the time. During the 10 minutes reading time between 8:50 and 9:00 hours, you need to go through the paper without writing as per the instructions for the exam. What you need to do, identify the questions where you can get easy marks, right? Those are the questions that you need to start with so that you collect as many marks as you possibly can as early as possible, so that you have got a decent amount of time to focus on those that will most likely, will be demanding. I wouldn't want to say difficult, where you need to apply yourself, think, try a lot of things. So you have a lot of time to do those once you start with the questions that carry a lot of marks. And it's to your advantage, once again, in terms of managing the time, right? Okay. Then the multiple choice questions, as you shall see as we move along, the multiple choice is 20 marks, right? So the 20 marks is across all the topics that we've listed that are covered in paper one. However, it's very important for one to also note that those questions are of different levels. Some are straightforward. It could be a case of whether you know or you don't. Some, they need you to apply yourself, and in many cases, they demand that you show this understanding more than anything else, right? So leave a decent amount of time to attempt multiple choice in case you decide to end with the multiple choice. Worst case, do not leave the multiple choice question unattempted blank, because there are options available for you to choose. As a result of that, when everything fails, there's a strategy that we shall talk to, which will also assist you in terms of maximizing the marks that you can collect, right? Now, speaking of definitions, which is the last bullet on the slide, the definitions they are indicated in the exam guide. Pay attention to the keywords, right? Not only are you supposed to, include the keywords, those keywords must be used in the correct context. What that simply means is that if I read the definition with all the keywords available, it must convey the correct scientific meaning, right? So it's the keywords which must be used in the correct context. So all the definitions are actually questions in which everyone must get marks. Now, the matric course is a 3-year course from grade 10 to grade 12, right? So some of the topics that you need to go back and remind yourself of. The first one from grade 10 is the principle of quantization of charge. If I can go to the formula sheet, the principle of quantization of charge would be your Q is equals to NE, right? So this equation, very, very important in electrostatics, because it kind of, gives us a sense of what the principle of quantization of charge says, to say that every charge in the universe is an integer multiple of the elementary charge. So remember that work from grade 10. And then when we talk about the principle or the law of conservation of charge, where we said Q net is equals to Q1 plus Q2, right? And then if we want two charges that have been brought into contact and separated, we know that the new charge that each one of them will have is Q net divided by 2. So that's what exactly the principle of quantization of charge actually says, right? Okay, and then in terms of motion in one dimension, we also looked at uniform velocity and uniform acceleration. Both are forms of uniform motion. Okay, in what way are these different? If, say, for argument's sake, we've got an object moving at 2 meters per second west. Now remember, velocity is a vector. What that says to us is that there's a component of magnitude as well as direction. So this object changes its position by 2 meters for every unit of time in which direction? West. So the 2 meters per second is the magnitude, while west is the direction. of change of position. Say, for argument's sake, we've got a uniform acceleration of 9.8 meters per second squared downwards. Okay, I'm using this deliberately because it takes us to your vertical projectile motion. Now, when we say an object undergoes or experiences a uniform acceleration, what that simply says to us is that the velocity of the object, which is the change in velocity per unit time, is equals to 9.8 meters per second every second. What that simply says is that in 1 second, the velocity of that object changes by a magnitude of 9.8 meters per second. In which direction? Downwards. So that's exactly, these are practical examples of uniform velocity versus uniform acceleration, right? So the data sheet will also be of very much important use for you there, right? And then the other one that we also looked at in grade 10 was the principle of conservation of mechanical energy, right? Which talks about mechanical energy between 2 points in a closed system, right? Suppose we've got the total mechanical energy of an object at position A, that must equal the total mechanical energy of the object at position B. Very, very important. This can only be applied if it is a closed system. How do we know that this is a typical example of a closed system? It's a case where we are told that you can ignore the effects of air friction. The surface on which an object is moving is frictionless or it is smooth. Then we can therefore say, yes, indeed, it's a closed system. We'll talk to a practical example of this one, right? And then we also looked at electromagnetic waves, right? Where we looked at the energy of a photon in as far as that equation. So these photons are packets of light energy, right? So the energy that a photon carries depends on the frequency, right? Which says, therefore, E is equals to hf. But while we know that the speed of light is c is equals to f times lambda, we also know that v is equals to f times lambda. So this is the general wave equation. Wave, it can either be sound, it can also be light, right? So if we talk about c, we're talking about the speed of light, you know. So this is with respect to, you know, EM radiation, while v, in the case of Doppler effect with respect to sound, we're talking about the constant speed of sound in air. So you know that c is equals to 3 times 10 exponent 8 meters per second. This is like 300 million meters per second, while v under normal circumstances would be your 340 meters per second, which explains why we say light travels faster than sound. Okay, so please make a distinction between those two. When do we use c? When do we use v? Right. And then we also went further in grade 10 and looked at series and parallel circuits. Very, very important. In a series circuit, the total or the equivalent resistance is determined using that formula, and that formula is given in the formula sheet, right? While for a parallel combination of resistors, we use that formula. However, I need to speak to this one where we have got only two resistors in parallel. R parallel will be equals to product, okay, over sum, right? So where is this coming from? It's coming from the very same equation of 1 over R parallel, but this is only applicable for two resistors in parallel. Because I would prefer that you use that if there are only two resistors. Why? Because quite often, some of you'd forget to flip that, because what you get on the right hand side is actually the reciprocal of the equivalent resistance, right? Okay, and then moving along again, in grade 11, quite a lot of stuff that was examinable. Remember the 4 Newton's laws, Newton first, second, third, as well as the universal gravitation. But central to it is also the application of those different laws. They carry a lot of marks. If you look at question 2 until question 5, it has everything to do with the Newton's laws, all right? We shall talk to examples of each of those, right? We also spoke about electrostatics in grade 11, as well as electric circuits as an extension to what we did in grade 10, right? Okay, without any waste of time, I briefly spoke about the multiple choice, 20 marks. It cannot be 5 minutes. Okay, so if it's 20 marks, it means you need to have a decent amount of time to do all the 10 multiple choice questions, right? Now, having said that, I'm going to use this as a practical example. If you look at this question, it's a velocity versus time graph of motion of an object under the influence of gravitational force only. Okay, I'm going to underline that. So if the object is moving under the influence of gravitational force only, this object is in free fall, and it could be a projectile. Now, if you look at this object, the initial velocity is v, positive v. Okay, that's our 0 there on the origin. Now, this object is both a projectile and it's free falling. What could be the reason for that? For us to justify that, we need to be able to distinguish between a projectile as well as a free falling body. So a projectile is an object, right, that is given an initial velocity. What we mean when we say an object is given an initial velocity, it means its initial velocity cannot be 0. Now, that can only be possible if an object is thrown up or thrown down, if it is launched. So if we launch it and then subsequent to that, it moves under the influence of gravitational force only, that projectile is in free fall, in the sense that only the force of gravity acts on that object, right? So, in other words, this is the free body diagram of a free falling object. Okay. Now, if you look at the graph, for the first t seconds of its motion, this object is slowing down. If it is slowing down from a velocity of v to a velocity of 0, we can immediately, deduce that this object was moving upwards. So it was thrown or launched vertically upwards with a speed of v. T seconds later, it came to rest. Okay, so while it was moving upwards, it simply means that this object was accelerating downwards. Why is it accelerating downwards? Because the only force acting on it is Fg, and its direction is downwards. So according to Newton's second law, we are saying that if a net force acts on an object, in this case the net force is Fg, if a net force acts on the object accelerates in the direction of the net force. So this object is, while it slows down going upwards, it's actually accelerating downwards, right? And then from t to 3t, ask yourself, what's the duration? Is 2t seconds, because the interval, so the time interval, that's why we talk about delta t. So for the last part of the motion, the object reaches the highest position after t seconds. Thereafter, it still accelerates downwards. If you check the gradient of the velocity versus time graph, in this case, which is change in v over change in time, it's negative 9.8 meters per second squared. Okay, so in this case, it means upwards was taken as positive because the initial velocity is plus v. Okay, so there's a lot in this graph that we can use just to demonstrate our understanding. But now the question talks about the displacement of the object after at time 3t, right? So there's two parts of the motion of the object: the motion of the object upwards, and the for a time delta t, time t seconds, and then the motion of the object 2t seconds, which is downwards. So from grade 10, when we looked at velocity versus time graphs or linear motion of objects, we said, or we agreed, that the area under the graph represents the change of position. Change of position of an object in a straight line therefore becomes the displacement. So the displacement in this case, okay, let me go back. Okay, so the displacement in this case is the area of this graph, right? So can I say it's delta y because it's vertical motion, right? Is equals to half. Okay, this is a triangle. So this upward motion is a triangle, is represented by the area of this triangle, which is half T V, right? So the upward motion from the point of launch until the highest position is Vt over 2, right? And then let's look at the motion downwards from the highest position is equals to still a triangle. So this is the other triangle, okay? Now we are not using equations of motion. We are using the graph to determine the displacement, right? So if you look at that, what do we have? We've got another triangle. Half the base in this case is 2t. Okay, where is 2t coming from? 3t minus t. That's the time interval. And then the height in this case is negative 2v, right? What does this give us? It gives us, if we cancel that, we are left with negative 2 vt, right? That's negative 2 vt. So the total displacement in this case, delta y total is equals to half vt minus 2 vt, right? Which obviously gives us negative 3 over 2 vt, right? So that becomes the solution, okay? Now, why did we choose this particular example to speak to the multiple choice? In this case, this is not a direct question whereby you just do, you know, your basic remembering or your calculation. You need to apply your mind to it. If you check the amount of time that we took just to discuss this question on its own, you know, it was not just a hit and run. So this goes on to justify the fact that for multiple choice, there needs to be enough time for us to do it, right? And then we've got another example on the multiple choice, right? Okay, it says an object moving at a constant velocity. I'm going to underline the keywords. This is exactly what you do when you answer multiple choice questions. So constant velocity and suddenly encounters a rough horizontal surface. Okay, the object continues to move over this rough surface. Now there are two parts to this problem statement. There is a part where the object moves at a constant velocity. Now the reason why we underlined the key term constant velocity is for us to speak to the science behind that. If an object moves at a constant velocity, we know that it is experiencing a zero net force. Okay, so the net force is equal to 0 newtons. Now, where is this coming from? It's coming from Newton's first law, because Newton's first law says that the object can either be at rest or it will move at what? Constant velocity. Okay, so rest, it means it is stationary, it maintains its position. Or, so the conjunction is or. It's either one of the two. So if in your maths it's mutually exclusive, it means you can't have an object at rest at the same time that object is moving at constant velocity. It can be one of the two, right? So when this object is moving at constant velocity, it is experiencing a zero net force. Does it mean there are no forces acting on it? Definitely not. Zero net force says to us that the total of the forces acting on this object is equal to 0 newtons, right? So the moment it encounters a rough surface, the big question therefore, let's say this object was moving eastwards. The big question then is, will the net force be still 0 on a rough surface? Definitely not. So there is a kinetic frictional force acting on the object. If the motion of the object is in that direction, okay, then the kinetic frictional force is in the opposite direction. Why? Because kinetic frictional force is an applied force exerted by the surface on the object in the opposite direction of motion, right? Now, the big question therefore that follows is, will this object still maintain a constant velocity? Definitely not. This object will accelerate. But in which direction is it accelerating? In the opposite direction of motion, because the net force acts in the opposite direction of motion, which is the kinetic friction. So once that happens, it says to us this object is going to slow down. So while it slows down, moving eastwards, it is accelerating westwards, which takes us back to grade 10. Right. So the question says the net work done on the object during the motion over the rough surface. Okay. Now, net work is total work. let's identify the forces that do work on the object while the object moves on the rough surface. So while it moves on the rough surface, that's the scenario. Okay, so it means there's kinetic frictional force acting in that direction, and then that's the displacement of the object as it slows down. What is the angle between these two? 180 degrees. Now, the kinetic frictional force is the only force that does work on the object in the opposite direction of displacement. So the amount of work that will be done by whatever that force is going to be negative. It can only be zero if the object was moving at constant velocity, because total work is done by the total force. In other words, what are we saying? Work net is done by F net. Okay, delta x cos theta. Right. So it can be very misleading. If you are quick to choose answers, you might be tempted to say zero because you saw that constant velocity. But subsequent to that, there was a surface on which that object moved on, which is a rough surface. Then, therefore, it's going to be negative. Brilliant question. Right. Okay. There can't be Newton's laws without forces once again. So the bigger part, the paper, is about Newton's laws. That's your vertical projectile motion, your Newton's laws in their own right, your work energy and power, your linear momentum and impulse. All these have to do with forces, and forces are actually captured in all the Newton's laws. Right. So the Newton's first law, we've spoken about that. The net force acting on the object is equals to zero. So how do you tell that an object is being acted upon by a zero net force? It's either the object is at rest or it's moving at constant velocity, according to what we've just discussed. And then Newton's second law, there is a non-zero net force. What does that mean? If we say when a net force, it means that net force cannot be zero. Okay? We are assuming that the net force is non-zero, because if there was a zero net force, the object maintains its position by staying at rest or moves at constant velocity, right? So if a net force acts on an object, the object will accelerate, right? But also what is important is that the acceleration and the net force are two vectors there. They have the same direction, because it is the net force that causes the acceleration, right? So the direction of the net force is exactly the direction of the acceleration of that object. But also important to it again is the impulse momentum theorem. Okay, right, very, very important. So if we have got this one is supposed to be F net, okay, delta t is equals to delta p. Okay, so this is impulse, right, which is equals to change in momentum. Let me repeat. Impulse is not change in momentum. Impulse equals change in momentum. Where is this coming from? When a net force acts on an object for a period of time, it will cause the object's momentum to change. Okay. Again, the other one that can also be a little bit of a challenge is F net is equals to delta P over delta T. Right. Here, what are we saying? This is rate of change of momentum, which is equals to the net force. That is change in momentum, which is equal to impulse. So you need to make a clear distinction between those two. And what's common between the first and the second law is that it talks about a single object. There's only one body, right? An object will remain at rest. How many objects do we have? One. For Newton's second law, if a net force acts on an object, how many objects are we talking about? A single object. But when we come to the Newton's third law, we are talking about two objects. There is body A and body B, right? Now, the force by A on B is equal in magnitude but opposite in direction to the force by B on A. So, if a force acts on an object and causes the object's momentum to change, it means the change in momentum of object A, whether it's a collision or it's an explosion, is equals to the change in momentum of object B in the opposite direction. Where is this coming from? F by B on A is equals to force by A on B in the opposite direction. So that's where exactly that is coming from, right? Okay, we shall look at a practical example which has to do with the applications of Newton's laws, right? We've got a 10 kg block that is connected to another block of unknown mass M, right, by a light, inextensible string. Okay, just to explain that, if the string is light and inextensible, it means we are not going to take into consideration the mass of that string. Okay, if it is inextensible, it means the string doesn't stretch, so there's a constant tension force between these connected bodies in the string. All right, the blocks are placed on a rough horizontal surface. I'm going to underline rough. What's the implication of the term rough? It says to us that there is a kinetic frictional force exerted by the surface on any object moving on that surface. So this kinetic frictional force is essentially a contact force which acts on the object exerted by the surface, right? So when a 45 Newton force is applied to the 10 kg at an angle of 30 degrees to the horizontal, the blocks accelerate. I'm going to underline accelerate. Which Newton's law is relevant in this case? There is some acceleration. It certainly means to us that, therefore, there is a non-zero net force acting on them, which causes the object to accelerate to the left. So the direction of the net force acting on this system is to the left. That's why the acceleration is also to the left, because the law in its own right says to us that if a net force acts on an object, the object accelerates in the direction of the net force. Done. All right. Okay, the block of mass M experiences a frictional force, constant frictional force of 1 Newton while it is moving. Okay, I'm particularly interested in the fluid body diagram. You need to get this very clear. You are going to draw quite a number of fluid body diagrams in physics paper 1. And essentially, this must be your easy marks, because yours is to identify those forces and label them correctly, right? Again, if you look at the mark allocation in this case, it's 5 marks. What does that tell us? There are 5 forces. For every correctly labeled force, you get a mark for that, right? So if it's 5 marks, there are 5 forces. If it's 3 marks, there is 3 forces, right? So this is a free body diagram. Now, this diagram is free of the body, right? So in place of the object, we shall draw a dot. The body is not there. What represents that dot? What represents the body is the dot. That's why we are saying it's a free body diagram, right? So let's identify the forces, right? Okay, there is that 45 newtons. Okay, many of you would be comfortable to say it's F applied. It's fine, even if you say it's 45 newtons, because all other forces are applied forces in any case, right? And here, you do not resolve the forces. You indicate the forces as they are. The examiner is very, very particular when it comes to that, right? And then what do we have? We also have the weight of the object, okay, of the 10 kg. This is W or Fg, right? That's 2. What else do we have? There is a force that is exerted by the surface on the 10 kg perpendicular to the surface. So that's the description of that force, because the object 10 kg rests on the surface. So what that says to us, there is a force that the surface exerts on the 10 kg perpendicular to the surface, and that's your normal force. Okay, there it is. And then what else do we have? We have, because this is a rough surface, there is a force that is exerted by the surface on the 10 kg, which is the kinetic frictional force. There it is. Okay, what else do we have? There is a string that is pulling block M. So between those two connected bodies, there is a force of tension. The tension on the 10 kg is to the left. Okay, right, this is not a scale drawing, so it's the magnitude of the forces of the vectors is not important. And then the tension on the object M is in the opposite direction, because it's the same string. So what do you have here? You've got how many forces? 1, 2, 3, 4, 5. That's how you get the 5 marks. Okay, so you haven't defined anything, you already have 5 marks from the onset. We're good to go, right? And then it says define the term normal force. Earlier on, I did indicate or allude to the fact that in any of these long questions, there will be a definition or two. So these are the easy marks that we need to grab by all means. Okay, so we want to define the term normal force. So it's either 2 marks or nothing there. Okay, what do we have here? We know that normal force is a contact force exerted by the surface on the object perpendicular to the surface. That's what a normal force is. So it's either you get the 2 marks or nothing. Right. Okay. 2.3, calculate the magnitude of the normal force acting on the 10 kg. Right. Then now you can resolve your forces, because the normal force acts on a vertical plane. So we need to pay attention to all the forces that are acting perpendicular to the surface. In this case, because we've got that force that's applied at an angle of 30 to the horizontal, it simply says to us, therefore, we've got the normal force acting in that direction, because that applied force, the vertical component of that applied force is actually lifting that object upwards. So this is Fy, right? And then we've got the W there, which is our Fg, right? So this is just with respect to vertical forces, all right? So if we want to determine, for argument's sake, in this case, the magnitude of the normal force, I want you to pay attention again to the mark allocation. If it was 3 marks, it was going to be formula, substitution, and answer. Now, we are given 4 marks there. It means we need to apply something before we actually substitute and calculate the final answer. What that simple says to us, are we able to get Fy? Yes. If we can be able to get Fy, because this is the horizontal component, and then that's the vertical component. That angle is 30 degrees, right? So if that's the case, so the vertical component is opposite to 30 degrees. So the vertical component, Fy, therefore becomes 45, sine 30 degrees, right? What is that? Sine of 30 is 0.5. So if we are looking for that, so you'd actually calculate the half of 45 there, which is 22.5. Okay, if I'm not mistaken, that's 22.5 newtons, right? Upwards. And then Fg is equals to mass times acceleration due to gravity, right? This gives us what? 10 times 9.8, which is what? 98 newtons, right? So we know that the sum of all the vertical forces, because there is no vertical movement whatsoever, this is motion in one dimension, so it means the sum of all these forces acting vertical is equals to 0, all right? So in other words, if you say a normal, plus Fy plus Fg, you must get 0 newtons, okay? And then after that, what follows is the maths. Not very important, right? And then you are able to say, okay, remember Fg and these two act in opposite direction. So if upwards is positive, it means downwards will therefore be negative, right? That's one just practical example, but key to problem solving on your Newton's laws, you need also to apply your mind, look at the keywords such as rough surface versus smooth surface. Rough, it means there's kinetic frictional force acting on a moving object. While it's smooth, it means the surface friction can be ignored, right? I've also mentioned something very important with regards to the mark allocation. If it's 3 marks, it's your formula, it's your substitution, and your answer. And remember, the answer must include the correct SI unit. If it is a vector, also indicate the direction, unless it says the magnitude of a vector, whatever the case may be. So pay careful attention to that. Okay, so vectors, direction. So a typical example of 4 marks says to us, it's a multi-step problem. It can be 4, 5, 6, 7, whatever the case may be. As long as it's not 3 marks, it's not your direct substitution and plug in values and then you use your calculator, right? Very, very important. Okay, and also the issue of the data sheet, right? This is where we got the formula of Fg is equals to mg, right? very important. This is where we spoke about the change in momentum equals to impulse, right? Then if we were to calculate, for argument's sake, the kinetic frictional force, we first determine the normal force. So do not immediately assume that the normal force is equal to the gravitational force. It will depend, like the case that we just saw in the previous example, right? Okay, multiple choice, another problem area, which I most definitely feel that if you really understand your stuff, you shouldn't battle, and worst case, you should not leave the multiple choice without any response or any answer for that matter. Okay, so you need to allocate enough time. We've spoken about the mark allocation for that. So the other trick to it is do not focus on the option that you think is correct. Think about a reason why the other three options are incorrect. But before you get to that, it's important that you also identify your typical distractors, those two options that will be totally out, and then you can choose from the remaining two. So that's the elimination of the distractors, right? So also pay careful attention to the terms that are written in bold or in capital letters, like constant velocity, smooth surface, whatever the case may be, because there is a lot of implication in terms of the science behind that. All right. So once you are done answering the multiple choice question, please go through your questions and look at your answers and ask yourself, have I answered the question? Because it's normal that you get carried away by something that yet the question asks, it demands the opposite of that which you know. So it's very important to check if you've answered the questions correctly, right? And then question 3 is on vertical projectile motion, right? We have spoken about the difference between these two, right? Those are the key terms. So if the examiner doesn't ask you to define a projectile or to tell us whether an object is a projectile or not, you can either be asked to define free fall, you can be asked to define acceleration, velocity, everything, all the way back to grade 10. So remember, free fall is the type of motion, right? Okay, in which the only force acting on the object is Fg. I've touched briefly on that. And then a projectile is an object. Okay, so you need to make a clear distinction between those two. A projectile is an object which is given an initial velocity and it moves under the influence of gravitational force only. So a projectile will undergo free fall, but not all free falling bodies are projectile, depending on whether the object was launched or not, right? And then we've spoken briefly about the 9.8 meters per second squared downwards, which is the constant acceleration or uniform acceleration that a free falling object experiences, right? So that's key. And then again, how do we tell that an object is actually in free fall or it's a free falling body? There will be a statement that says ignore air friction or ignore the effect of air resistance. That says to us, therefore, the only force acting on that object is the force of gravity, right? So Fg acts vertically downwards, which will be the direction of acceleration, right? So two things are very important, right? For a free falling body, number one, the only force acting on the object is Fg, or Fg is the only force acting on the object. As a result of that, the object experiences a constant acceleration. What do we mean when we say the object experiences a constant acceleration? Irrespective of the direction of motion, the acceleration of that object is 9.8 meters per second squared downwards. That's the key, all right? And then obviously the data sheet, very important. And then therefore this becomes the free body diagram of a typically free falling body, right? Okay, so when you approach the VPM, read this scenario carefully before attempting the questions. Don't say I've seen this before. Every question is unique in its own way. Take your time, try to understand, okay? Then you can apply what you know. In some cases, it will be important that you draw the trajectory. Trajectory is if you throw it from the top of a building, it will be like that. If you throw it from the ground to the top of a building, it could be something of this sort, right? It can be anything. So this trajectory actually assists you in considering motion between any 2 points, right? So remember, position, displacement, velocity, and acceleration are vectors. So direction is very, very important. So if we say upwards will be taken as positive, it says to us that downwards is negative and vice versa. All right. Okay. And then here is a practical example of a VPM question that maybe we can use as a discussion just to remind ourselves of what is important. We've got a small stone that is projected vertically upwards. This stone is launched vertically upwards, in other words. Okay. And then one would ask a question, is the stone a projectile or not? Then this is another way in which a definition can be asked, to say, if a stone is thrown from the ground, so there's a trajectory already that's accompanying this sketch. Now, if it is thrown at an initial velocity of 20 meters per second upwards, then it means indeed it is a projectile, right? And then on its way up, it reaches a maximum height A. On its way down, it passes the roof. It goes on and on. Of particular interest to us, ignore effects of air friction, right? So if we ignore friction, what are we saying? We are saying only force of gravity acts on the object. Question number 3.1, 2 marks, says write down the acceleration. Ask yourself, why is it 2 marks? Because acceleration is a vector. So you must indicate the magnitude as well as the direction. So our acceleration in this case, you can go to the data sheet, 9.8 meters per second squared downwards. Okay. So that's magnitude and direction, okay? Because we agreed that this is a free-falling body, therefore it undergoes uniform or constant acceleration. Now we are told, using equations of motion, because it's not a graph here, so we are able to use or to make use of the equations of motion, copy the equations as they are, do the necessary substitution, and then use the calculator, right? The time it takes for the stone to reach point A. Now, we can consider motion between the first point, let's call this the ground. Okay, consider the upward motion. Okay, the upward motion, and then we'll take upwards as positive, right? We're going to write that in full, obviously. Okay, so if we take upwards as positive, we ask ourselves, what do we have? We've got the initial velocity, which is positive 20 meters per second. Okay, we've got the final velocity at the highest position at A. So the initial position is A, is the ground, final position is A, then the object stops. And we also know the acceleration of this object is going to be negative 9.8 meters per second squared. Why negative? Because upwards has been taken as positive and acceleration is always downwards, right? So if it's 3 marks, it's simple formula, substitution, and answer, right? If that's the case. And then what do we have here? It takes the stone, the time that it takes the stone to reach point A. So we've got VF is equals to VI plus A delta T, right? So you can do a necessary substitution there. To copy this equation as it is, it's a mark, okay? Then the final is 0 is equals to 20 minus 9.8 delta T. And then you can do the necessary mathematics, right? Okay. Now, usually with the VPM questions, you actually use some of the answers that you obtained in the previous question in the follow-up calculation. Like in the case of calculate the magnitude of velocity of the stone at the instant it reaches point B, right? So you can consider motion from A to B, right? Because you've got the velocity at A, and then you are looking at the velocity at B, you know the acceleration between those. Or you can use the motion from the ground to B. The motion from the ground to B, if you consider motion from this point to that point, the change of position of this object, that's where the catch is. The change of position is 8 meters. Okay? Why 8 meters? Because from initial position to final position, 8 meters. The acceleration, while it moves between those 2 points, is still 9.8 meters per second squared downwards, which is negative. There it is. And then you can do the necessary calculation. So the moment you start doing the calculations, you've actually done the correct science. So spend a lot of time most of your time trying to understand why you use certain values, the time interval must be confined to the 2 points in which you consider that motion, right? So that's one practical example in as far as vertical projectile motion is concerned. And then when it comes to linear momentum and impulse, the following very, very key. Momentum P is equals to M times V, right? The product of mass and velocity. The definitions according to, Newton's second law, F net is equals to the rate of change of momentum, the net force acting on an object. So the data sheet will actually give you that. So you shouldn't battle in terms of trying to recall that. And we know that impulse is F net delta T, right? So this is the product of net force and time, which is, by the way, equal to the change in momentum. So we don't say impulse is change in momentum. Impulse equals change in momentum, and that's not the definition of what impulse is. In principle, impulse is product of net force and time, which is why the SI unit is Newton second. And remember, this is a vector, so you need to also include the direction, okay? Right. And then obviously the principle and also determining the nature of collisions, whether it's an elastic or inelastic, right? We've spoken about the Newton's laws is how they relate to the what you call the mechanics, right? Now, when it comes to impulse and momentum, nothing changes. Read carefully the scenario, underline the keywords. Remember, velocity, momentum, change in momentum, average force are all vectors except for time, right? So you must take direction into account because these are vectors. The formula sheet is provided for your use, okay? Also pay attention to the mark allocation, right? 3 marks, formula substitution answer, nothing has changed, right? Now, here is a practical example of linear momentum and impulse, okay? I've put that deliberately there because that's where the wheels come off. That's where we lose it, okay? Then we've got 2 trolleys there, A and B, of mass 2 kg that are held stationary on a smooth horizontal surface with a compressed spring between them, right? Trolley A moves to the right at a constant velocity of 5 meters per second and collides with the wall. So if trolley A collides with the wall, during that collision, trolley A exerts a force on the wall. Simultaneously, the wall exerts a force on trolley A, right? So the first one says define an isolated system for 2 marks. It's either you know or you don't. So it's all or nothing. So when we talk about an isolated system, it is a system in which the total external forces or the net force equals to 0, right? That's what the examiner wants when it comes to you defining what an isolated system is, right? And then calculate the velocity of trolley B immediately after the spring is released, right? Right. So this is an explosion, right? Why are we saying this is an explosion? Okay, the spring is loaded. The moment we release the spring, it exerts equal forces on trolley A and B simultaneously in opposite direction. So that's our Newton third law, right? We must remember that. Okay, so if we want to calculate the velocity of trolley B, we must choose and say maybe to the right is positive, meaning that to the left is negative, right? So in this explosion, we know that the total linear momentum before the explosion equals the total linear momentum after the explosion. That's where it all begins, right? So once you apply this and you take direction into account, then the rest obviously is the mathematics because it comes in with the substitution, provided it can only be correct provided you actually took direction into account, right? So you want to calculate the velocity of trolley B immediately after release, right? So we are told that trolley A moves to the right. So in other words, what we have before the explosion, the system is at rest, okay? That's 0 total linear momentum, okay? So in other words, the momentum of trolley B plus the momentum of trolley A after the explosion must be equal to 0. So what that simply says, without maybe going into the calculations and deeper, it means that when you add the momentum of trolley A and trolley B after explosion, it must be 0. That can only be possible if the momentum of A is equal in magnitude to the momentum of B, but opposite in direction, that's when we can get zero. Where is that coming from? It comes from the Newton's third law. Why is that so? Because during that explosion, the spring exerts a force equal in magnitude on both trolleys in opposite direction, which says to us, therefore, the change in momentum of trolley A equals to the change in momentum of trolley B in opposite direction. With that said, we shall take a short breather. Then when we come back after 5 minutes, and then we will continue from there with our discussion. See you after the break. session once again. We say going into our second and final segment of our last push. We'll take this opportunity to look into work, energy, and power, and just remind ourselves of what is important once again. The following definitions, very, very important. Work done by a force. It's just not work done. It's work done by a force, because what does work on an object is a force. So it's work done by a force equals to the force displacement cos theta. So theta is the angle between the force and the displacement. As we had demonstrated earlier on, if the kinetic frictional force acts on an object, the displacement of the object is in that direction. So in this case, the angle is 180 degrees, which means cos 180 equals to -1. That's why kinetic frictional force does positive work. While we have got an applied force in the direction of displacement, so the object is displaced that way. Let's say there's an applied force, so theta in this case is equals to 0 degrees. So cos 0 degrees is equals to +1. So that's why we have got a force that does positive work. So this force acts in the direction of displacement as it does work. And then the principle of conservation of energy, we spoke about it. It's the principle of conservation of mechanical energy. As we know it, E mech at a point equals to E mech at another point. It could be B. So the total mechanical energy, provided it's a closed system, it will remain constant. And then we've got the work energy theorem. The formula sheet will indicate W net is equals to delta EK, right? And then also be able to distinguish between a conservative and a non-conservative force. And then the last part of this one is on power, which is P is equals to W over delta T. But also remember this formula, P average is equals to FV, right? Where V is the constant speed or the constant velocity, right? Here is a practical example of a scenario on work, energy, and power. We've got a skateboard, a person on a skateboard on a track, okay, which is at a vertical height of 15 meters as indicated. It comes to rest at point D after it slides down, okay. Section A and B is frictionless. It means mechanical energy at E mech, okay, at A equals to E mech at B. And remember, mechanical energy of an object is the sum of the gravitational potential energy and kinetic energy of an object, right? And then we're told that it moves from B to C, and then from C to D, mechanical energy will not be conserved. Why? Because it is a rough surface. There is a non-conservative force acting on the object at that point. And then 5.1 for 2 marks, all or nothing, state the principle of conservation of mechanical energy. So in a closed system, the total mechanical energy of an object remains constant, right? Straightforward. And then calculate the kinetic energy of the skateboard at point B. So this is 3 marks. It's your typical routine calculation. So we are going to apply the principle of conservation of mechanical energy to calculate the kinetic energy, right? Now, we know that E mech at A is equals to E mech at B, which is your mgh, okay, plus half mv squared is equals to mgh, okay, plus half mv squared. So this is at 2 points, at point A and at point B, right? So this is at B and then this one is at A, right? What do we know? If it starts from rest, there is 0 kinetic energy, right? So it will be the mass of the boy in the skateboard is 55, 9.8 multiplied by 15, okay, plus 0 because it starts from rest, equals your mgh at point B is 0 because it's on the ground, plus ek final, right? We want the ek final, which is at point B. And then when you do your maths there, you'll get your value of ek final. But it's very important that you show the zero substitution so that you can get all the marks for substitution, because the instruction says show all your calculations. So because this is 3 marks, it's your formula, substitution, and answer. And then now there are already 2 definitions in this question. State the work energy theorem. So for definitions in this case, in one question we have got 4 marks, right? Okay. In addition to that, you might also be asked to draw a free body diagram. So those are other 3 marks, because yours is just to identify the forces. So if you state the work energy theorem work energy theorem for 3 marks, it's all or nothing. And then I just want to draw your attention to this one. When you use energy principles, there are 3 energy principles. Okay. There is the principle of conservation of mechanical energy, okay, which we have spoke about. Okay, we have also the principle of, the work done by a non-conservative force. Let me just go to the energy principles. So this is the principle of conservation of mechanical energy. Then the other energy principle is the work energy theorem. And then the other one is the work done by non-conservative force. This is actually the work done by the kinetic frictional force, which is F kinetic delta X always is cos 180 degrees. Why? Because the kinetic frictional force acts in the opposite direction of displacement. So non-conservative, it means there will be a change in kinetic energy. If it's conservative, it means the mechanical energy remains constant, right? So when the question says use energy principles, do not be tempted to use equations of motion. So it could be any of those 3, energy principles. Now, but remember, you can only use the principle of conservation of mechanical energy when it's a closed system, right? Whereas the work energy theorem and the work done by non-conservative force can be used in any other case, right? Very important. And then let's look at something on electrostatics, right? We have already indicated that from grade 10, we know about these 2, the principle of quantization of charge and the principle of conservation of charge. In grade 11, we looked at the rest of it, okay? So it is examinable in grade 12 as it is. So this becomes your Coulomb's law, right? This is your electric field at a point. And then this is the principle of quantization of charge, right? So from this definition, for argument's sake, you know that E stands for electric field at a point. It is the force per unit positive charge. So this equation actually gives you the definition of what electric field at a point is. And then once again, this equation Q is equals to NE. It gives you the principle of quantization of charge, right? Okay, let's look at a practical example. We've got 2 point charges P and T that are placed 0.03 meters apart. So take note, 0.03 is already in SI unit. So there is no conversion whatsoever that is required. Okay, so the charge on P is plus 36 times 10 exponent minus 6 coulombs, which is like 36 microcoulombs, while T is half that with an unknown sign, okay, whatever that sign is. So it's either positive or negative. And then the definition, as we have indicated earlier on, 2 marks, all or nothing. The electrostatic force between any 2 point charges is directly proportional to the product of the charges, okay, Q1, Q2, and inversely proportional to the square of the distance between the charges. So that equation captures the mathematical relationship between product of charges and the electrostatic force, square of the distance, and the electrostatic force, right? And then draw an electric field pattern, okay, around a positive charge for 3 marks. Okay, so for any positive point charge in space, okay, there is a field that exists around it, okay, a non-uniform field that exists around it, right? There is the field. So in this field, if we place a unit positive charge, in which direction will it experience a force? Away from that charge which creates the field. So it will repel the unit positive charge. So that's why the direction of the field is like that. So the 3 marks in this case is that the lines must touch the surface of the charge. Okay, that's 1. The direction must be correct away, right? As well as these lines must not cross. So that's where you get the 3 marks. Okay, so it's easy marks. So for the negative one, it obviously is to be the same pattern, same shape, only opposite direction, right? And then 7.3, calculate the magnitude of the force that P and T exert on each other, right? The magnitude of the force it doesn't say it's attraction or repulsion because we don't know the sign of charge T, but we are interested in the product. So if it's 3 marks like this, it's going to be your formula. F is equals to K Q P multiplied by QT over R squared. So for copying this formula as it is from the data sheet, you get a mark for that. Okay, and then for substituting correctly, you'll also get another mark. So when you substitute the magnitude of the charges, the trick is to not include the sign even if the sign of T was given, because we are only interested in the magnitude, and we know that if charges are opposite, they would attract each other. If they are like or similar, they would exert a repulsive force on each other, or they would push each other away. So that's those are easy marks that each and every one of us must be able to actually collect, right? And then when it comes to the other work in grade 11 on electric fields, right, we've got 2-point charges there, spheres M and N. They are at a distance of 0.15 meters apart. Okay, they are on insulated stands, right? Meaning that this is a closed system. So the net charge in this closed system must essentially remain constant. Okay, and then P is a point, while we've got 2 charges M and N. Now we're told that N carries excess. Okay, now if N carries excess charges, it means excess electrons, it means N has acquired a negative charge. It can only be positive if electrons were removed from it. Okay, right? So N is negatively charged. Okay, and then calculate the charge on N. Now this is purely based on the principle of quantization of charge. Why? Because we know that Q is equals to N times E. So N is the number of electrons in excess or electrons removed. So in this case is 5 times 10 exponent 6 multiplied by the elementary charge. Please do not confuse the charge of an electron to the mass of the electron. So read the table of physical constant correctly. The mass will be in kilograms. The charge will be in coulombs. Here we're talking about the elementary charge because it's excess. There's a negative. So we put the negative 1,6 times 10 exponent negative 19, right? And then you can calculate the value of Q. Okay, so the 3 marks is for formula, the substitution, and the correct answer with the correct SI unit, which is the coulomb. Okay, whatever that is. All right, and then define electric field at a point. If you go to the formula sheet, it says E is equals to F. Okay, it says E is equals to F over Q. Take note, that's a small q. So that says to us electric field at a point is the force per unit positive charge. So the most part that is important that you often forget is per unit positive charge. Even if you go back to the electric field around a positive point charge, we place the unit positive charge to determine the direction of the field at that point. So the force that will be experienced by the unit positive charge placed at that point is actually the electric field at that point, right? So that's why it's gonna be 2 marks there. Then draw the electric field pattern due to charges M and N. So M is positive, N is negative. Remember, it's positive, negative. Okay, so these are unlike or opposite charges. So it's the direction is from positive to negative. Okay, so the direction must be always from positive to negative. So we have something of this sort. Okay, so this is towards, away. Okay, this is towards the negative. Okay, away from the positive, right? That's 3 marks. So also know that even if we swap them, The only thing that's going to change here is the direction. It's always away from the positive towards the negative, right? So that's 3 marks there. And then calculate the magnitude of the net electric field at point P. Guys, this is a multi-step question. What makes us say that? Because it's 5 marks, right? So if it's 5 marks like this, it means we have to, first of all, because we're talking about the net, so we have to place a unit positive charge at point P, right? So this is the point P there. At point P, what do we place? We place a unit positive charge, right? Now, we ask ourselves that if we place a unit positive charge at point P, due to charge M, in which direction does it experience a force? Remember, M is positive. Unit positive charge is also positive. So the positive charge will be repelled by M in that direction. Hence, at that point, it will be E due to M. Okay? And then, same unit positive charge due to N, it will be attracted towards charge N, because charge N is opposite to the unit, the charge of M is opposite to that of the unit positive charge. So this is E due to N. Then we can go on and use our vectors. If we take that one as positive, it means onto the left is going to be negative. Therefore, E net in this case will be equals to E due to M minus E due to N. Then what follows after that is the mathematics, because we know that E is equals to KQ over R squared. Remember, P is 0.25 meters away from M. At the same time, P is 0.1 meters away from N. So the science part of it is exactly this, which is what we need to focus our attention on. Okay, so these are actually marks that each and every one of us can actually collect, but we need to pay careful attention to the vectors, right? So that's as far as electrostatics. And then the other very, very important concept that I genuinely feel that we can also grab a lot of marks is on electric circuits as we know them from grade 10 all the way to grade 12, right? In terms of definition, remember EMF, what EMF is? EMF is actually the maximum energy that can be dissipated by a battery per coulomb of charge, because it comes from V is equals to W over Q. So it's the maximum energy or maximum work done per coulomb of charge. Okay. Then we've got terminal potential difference, which is your V external. Okay. Once we close the switch and there's a current in the circuit, then we have got terminal potential difference, which we normally refer to as V external. Okay. Internal resistance, if it's not ignored, remember there's also the application of Ohm's law, series and parallel circuits as we know them from grade 10, as well as power, right? Okay, now that's the data sheet that captures the very, very important concepts. That's our Ohm's law, which in some cases we'll write as V is equals to IR. Okay, and again, this side, if it says EMF, okay, is equals to I R plus R. That's what it is. This is your V is equals to I times R. The only difference here is that we've taken into account the internal resistance. So it still captures the Ohm's law as it is. So we're still consistent. And the variations of the power formula, okay, in the context of circuits. Right. Now, let's look at a practical example of an electric circuit that may be asked. It says here a battery with an EMF E and an internal resistance of 1 ohm. Now, in this case, the internal resistance has been given, right? In some cases, it may not be given. The same applies to EMF. It can be given or not given. Whatever the case, it's not a transmesh. It's okay, right? It is connected to 4 resistors as shown. Switch S is closed. There is a current of 0.5 amperes that passes through the 6 ohm resistor. Okay, I want you to look at the 6 ohm resistor and the 12 ohm resistor immediately. What's the relationship between 6 ohms and 12 ohms? You can immediately think of it in terms of, 6 is half 12 and 12 is double 6. Okay, so the current that goes through the 12 ohms must be half the current that goes through the what? The 6 ohm, because the potential difference is, so V across 6 ohm is equals to V across 12 ohm. What could be the reason for that? Because that's a parallel combination of resistors. Okay, so that comes from your grade 11 Ohm's law. All right, and then it goes further and says state the Ohm's law as we have predicted. So when they say study the circuit below, you need to understand the circuit first before you even look at the questions. Like we've predicted definitions, it will be the first question: state Ohm's law for all or nothing. Right, now the Ohm's law, what does it say to us? The potential difference across the ends of a conductor is directly proportional to the current provided temperature remains constant. So we need to qualify, when is V directly proportional to current? Only when the temperature is kept constant, right? Now it says to us here, calculate the reading on A1. Calculate the reading on A1. So A1 is actually the current that goes through the 6 and 12, the same current that goes through the 20 ohms. Okay, so 20 ohms is in series. Okay, because if we trace this, when the current starts from the battery, it goes that way. When it reaches here, it splits. Okay, right. So if there's 0.5 amperes here, here it's 0.25. Okay, so the current passing through 12 ohms is equals to 0.5 plus 0.25, which gives us 0.75 amperes. Right, so the 0.75 amperes is the current that passes through that. Okay, so 20, in other words, 20 ohms, the current that passes through 20 ohms is actually 0.75 amperes, right? And then that's why this is 3 marks. It's actually formula substitution and answer. Okay, you can calculate V parallel here for 6 ohms, which is equals to V for 12 ohms, as we had earlier indicated, right? Okay, and then calculate the reading on A2 when the power dissipated by R is 16 watts. Okay, now this is also 3 marks. Okay, we've got the power, okay, of R. We want the current passing through that. All right, now you immediately think of it in terms of, yes, if we have the total current passing through, if the current meets here, is the total current that will pass through the battery. Okay, now power, we know that P is equals to VI, right? So this is the power of R. So if we know the voltage across R, we will also know the current that passes through R, because we are given its power, right? Now, if we are able to calculate the voltage of 20 ohms, V 20 ohms, okay, is equals to the current times resistance. Okay, the current passing through 20 ohms is 0.75, okay, multiplied by 20. Okay, so whatever that is, okay, you'll get this voltage, okay, this V, and you add it to V parallel. Okay, this is our V parallel. Okay, so in other words, if let's call this V1. In other words, V1 plus V parallel, okay, is equals to V across R. Okay, what that simply means is that these two, if we consider this as a single resistor, it is in series with the 20 ohms, right? So if we add them, they are in parallel with R. That's why the total voltage of V parallel and V1 must give us the voltage across R. And then we can go back to this formula of P is equals to VI. However, there will be variations of, different ways in which you can calculate power. But the point that we're trying to make, when it comes to any circuit, make sure that you study the circuit carefully. Understand the relationship between resistors in that particular circuit. It could be series, parallel, or a combination of the two. Once you get that right and you understand that in a series, current is the same, and then in a parallel combination, the current is divided, and the opposite is true for voltage. Then you are able to actually work your way out. Okay, because of time constraints, the moment it talks about EMF, it will take us back to the formula E is equals to I R plus R, of which at this time we would also have calculated the resistance of R, so that we have the total resistance in the circuit, so that we can be able to substitute that, and that is given if we have the current, and then we can always get the EMF of the battery. In this case, the EMF was unknown, right? So that's one practical example when it comes to to the circuits. And then the other question that is of particular interest to us relates to the electrical machines, your motors and generators, right? So remember, Faraday's law explains the electromagnetic induction, right? So the principle on which generators operate is the principle of electromagnetic is the electromagnetic induction as explained by Faraday's law, right? The magnitude of induced EMF, is directly proportional to the rate of change of magnetic flux. So we won't be doing those calculations on Faraday's law. However, we must be able to use the Faraday's law to identify the factors that affect the magnitude of induced EMF. Okay, the strength of the magnet, the speed of rotation, the number of turns in the coil, right? So those are the three most important ones. And then when it comes to motors, we talk about the motor effect. Okay, the motor effect is if we've got a current carrying conductor and we place it in a magnetic field, it would experience a force. So that movement is a result of electrical energy being converted to mechanical energy, right? Which is the opposite with generators, which is from mechanical to electrical, right? And then that's as far as electrical energy transformation rather. And then when it comes to the rules, we apply these rules. Fleming left-hand rule for motors, okay, we'll apply in one of the cases that we'll just look at now. And then the right-hand rule is for what? Is for the generators, okay? And then there will be also problems on alternating current. This is for alternating current generators, right? And then just one last particular example that I want us to use with respect to the previous slide. We've got a simplified sketch of an AC generator. I want to highlight that this is a generator. Why are we saying that? Because we are told that it's a generator. So we mustn't get ourselves confused. So read the problem statement carefully and understand. It's with a coil that is initially in a horizontal position. There's magnets, there's the conductor X and Y. Those are 2 points in the coil. We're given the direction of induced current, okay? And then when the coil of the generator rotates clockwise, right? I'm going to underline that the 2 poles of the magnet, between the 2 poles of magnet, the direction of induced current is from X to Y, as shown above. Now, is A North Pole or South Pole? First of all, we ask ourselves, is this a motor or a generator? Fortunately, we have been told it is a generator. So if it's a generator, we'll apply the right-hand rule. So if you look at the rotation, I'm going to focus my attention on the XY, right? So if I use my right hand, that's the direction of motion. So the part of the coil XY moves upwards, okay? The direction of the field is north to south, is pointing in that direction, okay? And then the current is from X to Y. Now, the question is A the north or the south? Obviously, A becomes the North Pole, okay? And then this one becomes the south, because the direction of the field is that, if we apply the right-hand rule. So that's why this is just one mark. Either you know it or you don't. And then the coil is allowed to rotate 180, and we're told it's an AC, okay? Will the direction of current be from X to Y or Y to X? In this case, we know that in every half revolution, the direction of current is reverse. So that's gonna be very, very important for you to remember. So if you reverse, that will be from y to x after every half revolution, right? And then sketch the EMF time graph, okay, for the two complete rotations. This is an AC, okay? It's starting at the position of the diagram, okay? Remember, so this is EMF in volts, that's time in seconds. So when the coil is horizontal and then it's lying parallel to the field, at that point it induces the greatest EMF, because while it's lying parallel to the field, it's moving perpendicular to it, meaning that it will start with the maximum induced EMF. Okay, right, that's 90. Okay, that's 180. 270, that's 360. So this is one revolution. So we have to double that because of space. So in other words, it could be something like this. Okay, that's okay, 1, 2, right? So because of time constraints, I think you get the long and short of it. The only question that we did not try to touch a little bit of it was on photoelectric effect because of the time constraints. So today is the eve of the exam. We're not going to sleep very late. You need to be refreshed. Take it easy. Do the easy stuff, and just to boost your confidence. I most certainly hope that the session did indeed benefit you in terms of your readiness. From myself, Temba Ngcuba, I just want to wish you everything of the best, and goodbye for now.